Hello, good morning.
Good morning. Good morning, Tiffany.
Hi, Tiffany. Good morning.
Hi.
Hi.
Hi, Ramu. Nice to meet you.
Nice to meet you too.
All right. Hey, Prem.
Hello. Hi. Good to see you.
Hey, good
Hi.
to see you again. All right. First session of the day
Yes.
with rested minds ready for more.
And you are tired, I think, because it's evening time.
Yeah, I just quickly had some dinner, so I'm going to try to relax now. Yeah.
6:30.
Yes, coming up on 6:30. Yeah, actually, it seems like there's enough light. I do have one more light I want to adjust.
No, light is good enough. The light is good enough.
Let me try one more.
Okay, sure.
All right, there we go. Should I go ahead and share my
Yeah, you
slides
can
now?
try
or
sharing
is-
this. Yeah,
Yeah.
you can try
Okay.
sharing the slides. Yes.
Okay.
Yeah, I can see.
All right. There we go. And should I just leave it up here, or is there something else you want to show
No, it's fine.
before me? Okay. There we go.
Will you be traveling to Asian side later this year?
Prem, I don't have any trips to Asia planned.
Oh, okay.
Yeah. Yeah, it's not happening this year,
Mhm.
unfortunately. I think the longest distances for me, I did do a trip to Europe in the summer, and then in November,
Mhm.
I will go to Argentina.
Okay.
Yeah. It's great. You have two other distinguished lecturers in your program for this event.
Yeah.
I have yet to cross paths with them, so I guess this is my crossing of paths with them so far this year.
Okay, because of the timing, I think maybe Orlean may not join this meeting. His time is different.
Oh, okay. Okay.
Yes. Maybe a physical meeting is the best one to cross path.
Okay. So good morning, everyone.
People, maybe we wait for a few minutes.
Okay.
Ramu, are we saving questions to the end, or are we welcoming questions during the talk?
I mean, conventionally, like the questions will be asked after the presentation, after the talk.
Okay.
Yeah. So is this okay for you? I mean, is it comfort with you?
Yeah, that's fine. That's fine. And this audience, is it students and postdocs or other professors? Or who am I speaking with?
Mostly postdocs and students.
Okay.
Yeah. Maybe we can start now. People are coming and
Okay. So good morning, everyone, and welcome back to the second day of the ongoing IEEE Magnetic Symposium. My name is Bipul Kumar Mahato, the session chair of this plenary session. The first talk will be given by Dr. Tiffany S. Santos, Director of Non-Volatile Memory Material Research, Western Digital Corporation, San Jose, California. So the plenary session will be 50 minutes plus 10 minutes. And her title of the talk is Spin, Beats, and Flips, Essentials for High Density Magnetic Resonance Memory. So let's for the talk.
Okay. Okay, thank you for that kind introduction. Good morning, everyone. It's evening for me, but I hope you got some good rest after the first day of this event and ready for the second day. And I'm happy to kick it off with my talk. This is a distinguished lecture talk, and I'll say just a few words about the IEEE Magnetic Society before we get started. And by the way, my talk is about 45 minutes long, so there will be some time to do questions and answers afterwards. And I very much like to hear from you and get your questions then. So The IEEE Magnetic Society is the leading organization for bringing together people that do research in magnetism. And there are active local chapters all over the globe, just like this one, bringing to you this event today. And the IEEE Magnetic Society also organizes major international conferences focused on magnetic materials and applications. This is the Intermag conference and the MMM. And the society offers financial support to students traveling to attend these conferences. So if you're not already a member, I encourage you to go to the website and see what the society has to offer and consider joining to be part of this great community. So I am at Western Digital. The headquarters is located in San Jose, California, and Western Digital is a data storage company. There are two main products for Western Digital in mass production. One is the hard disk drive. That is a magnetic data storage device. And the other is based on NAND flash. That's the solid state drive. But I'm really not going to spend any time talking much about those today. What I'm really excited to tell you about is the research that we're doing on Imram, magnetic random access memory, in the research division of Western Digital. So in this talk, I'll start out by giving a history of the magnetic tunnel junction. And I'll spend some time on this because the magnetic tunnel junction is a key element in these major applications that I'm going to be talking about, the hard disk drive and magnetic random access memory, MRAM. And then I'll give an introduction into spin transfer torque, MRAM, and I'll discuss the challenges that we're facing as we're trying to progress toward a high density STT MRAM technology. I'll give a couple of examples of experiments that we're doing in our research lab to address these challenges. One is engineering the free layer to switch at lower current. And the other is a nanofabrication experiment working to make very small MRAM bits very close together in an array. And then I will conclude. So a great place to start talking about the history of the magnetic tunnel junction is with Ivar Gavar. And here he is standing at the blackboard here. He is a scientist at General Electric in New York State in the late 1950s. And he wanted to study conductance between metals. So he had the idea of using an aluminum electrode and using its natural oxide at the surface, aluminum oxide, as a tunnel barrier. So Ivar Gavar, he was trained as a mechanical engineer, but he found himself among physicists and started taking physics classes at the local college. And they just started getting onto the superconductivity chapter. So he had the idea of putting a superconducting lead counter electrode here to form this tri-layer tunnel junction. And with this tunnel junction, he showed the energy gap in the superconductor measured by electron tunneling from the aluminum into the lead superconductor. And this was a remarkable verification of the BCS theory. And for this, he was awarded the Nobel Prize in Physics in 1973. Then a few years later at the Francis Bitter Magnet Lab at MIT, Paul Tedrow and Robert Messervy, they were also using aluminum electrodes and aluminum oxide tunnel barriers, but this time the aluminum was a superconductor. And they had the idea of using a ferromagnet, nickel, as the counter electrode. And what's special about ferromagnets is that you have this asymmetry of the density of states according to spin. And so with this tri-layer tunnel junction, they showed the asymmetry of spins tunneling from the Fermi level of the nickel into the aluminum superconductor. And this was the first experiment showing that spin is conserved in the tunneling process. And this is something that we take for granted today, surely, because now we have applications of this. But this was really the first experiment showing it. And it broke open this field of spin polarized tunneling. Then a few years later, in France, there's a PhD student, Michel Julier, and he was inspired by the work of Messervy and Tedrow. He had met them at a conference in Europe, and for his thesis work, he introduced a model for tunneling between two ferromagnets in a magnetic tunnel junction. He proposed iron and cobalt ferromagnetic electrodes separated by a thin insulating tunnel barrier. Tunnel barriers are just 1 to 2 nanometers thick. And he used this tunnel junction, a magnetic tunnel junction, in an experiment as well. So he had learned from Messervy and Tedrow that spin is conserved in the tunneling process, and therefore there should be two well-defined resistance states for when the two ferromagnets have their magnetization oriented parallel to each other. You have a lot of spin up electrons here at the Fermi level in one ferromagnet, and a lot of empty spin up electron states for them to tunnel into in the other ferromagnet. And this leads to a high tunnel current and correspondingly a low resistance state. But when the two ferromagnets have their magnetization oriented anti-parallel to each other, there's this mismatch of the density of states, and thus this leads to a low tunnel current and correspondingly a high resistance state. And Julier defined a tunnel magnetic resistance ratio as the difference between the anti-parallel and parallel state, or the high resistance and low resistance state, over the resistance of the parallel state. And for his thesis work, his tunnel junction using amorphous germanium tunnel barriers had a TMR ratio of 14%, just at low temperature, at liquid helium temperature. But when he did the experiment at room temperature, there was no TMR. And there was no TMR at room temperature until 20 years later. This team here gave the first demonstration of TMR at room temperature, and they published their work in 1995 in Physical Review Letters. So the PI of the study was Dr. Jagadish Mudera here. And as a co-author, there's a high school student, Lisa Kinder. This was a very ambitious 8-week summer project assigned to her when she was visiting the lab as a summer student. Also as co-author, Terilyn Wong. She was a freshman undergraduate student at MIT. And then Robert Messervy, he was retired at the time. So it's a fun example of these scientists at all levels of their career coming together to make this important discovery. And at the same time, Professor Miyazaki and Tezuka, they also observed TMR in their experiments at room temperature. This was using aluminum oxide tunnel barriers in between cobalt and cobalt iron electrodes. And it was this discovery alone that led to the major applications that we have now. Magnetic tunnel junctions can be used as a magnetic field sensor. This is how it is used in a hard disk drive. And it can be used as the basis of a memory, as it is in magnetic random access memory, because it has these two well-defined resistance states depending on the relative orientation of the ferromagnetic electrodes. But before I say a few more words about these applications, I want to cover a couple more important milestones for magnetic tunnel junctions along the way. In 2001, there was a first principles calculation saying that if you use iron electrodes and magnesium oxide tunnel barriers, you'll get a special situation that when you have an epitaxial arrangement of the atoms across the interfaces between the iron and the MgO, you'll get fully spin polarized electrons in the iron, so polarization 100%. And for these fully spin polarized electrons in the MgO, you'll get a lower tunnel barrier height, letting it be easier for them to tunnel. So this combination could lead to TMR ratios approaching 1,000%. So this was very motivating for experimentalists getting better and better at making high quality magnetic tunnel junctions. And sure enough, just within a few years, published in 2004 in the same issue of Nature Materials, there is demonstrations of very high values of TMR with MgO tunnel barriers at room temperature. This was done by Shinji Yuasa and colleagues, showing TMR of 180%, and Stuart Parkin and colleagues showing TMR of 220% with MGO tunnel barriers. And as the work progressed to try to get higher and higher TMR, now you can see upwards of 600% with MGO tunnel barriers at room temperature, whereas the best values you can get with amorphous aluminum oxide tunnel barriers is around 80%. So this brings me to the applications. So magnetic tunnel junctions were first used in hard disk drives as the key element in the read head. This was first introduced by Seagate in 2004. The tunnel barriers at this time were titanium oxide. And the other application, the magnetic tunnel junction, is a key memory element in toggle Imram, magnetic random access memory, first introduced by Freescale, now known as Everspin, in 2006. So I'll say a bit more about these applications. So we are all using hard drives pretty much on a daily basis. So this means that we're using magnetic tunnel junctions on a daily basis. And this is because, I mean, if you're using Facebook or Instagram, if you're uploading pictures there or to Google Photos, or you're backing up your data to the cloud, or you're even watching a YouTube video or Netflix video, there is a magnetic tunnel junction in a hard drive in a data center in some remote location, reading the data for that video off the disk of the hard drive and bringing it to you, the user. And I'll say a few words about how this process works. So I'll describe how the magnetic tunnel junction functions to read the data off the disk of the hard drive. So I'll introduce the hard drive. Here it is here. The two main components are this disk here, spinning rapidly here, and it's made up of a shiny metal magnetic film coating the surface, the top and bottom surface of this disk. If you take a closer look at this film with a powerful microscope, you'll see that it is a network of magnetic nanoparticles. And groups of these magnetic nanoparticles are magnetized together to form a bit of data. Zeros and ones magnetized up and down. This is shown schematically here in these red and purple colors, showing a schematic of the bits written on a track. The other main component of the hard drive is the head, and it's located at the very tip of this arm. As the disk is spinning, the arm has a motor allowing it to sweep back and forth, and so that it can access any point on the surface of the spinning disk. And the head is made up of two main components. This is the writing component, which writes the perpendicular magnetization in the bits onto the media. And then the reader part of the head, this is where the magnetic tunnel junction sensor is. So the perpendicularly magnetized bits on the media, they have stray fields coming into and out of the surface of the bits depending on their orientation. And this stray field is what the magnetic tunnel junction is sensing. So this is shown schematically here. You have the up and down magnetized bits shown schematically here in the orange and black colors. And then you have the magnetic tunnel junction here. The white layer is the tunnel barrier. Then you have a ferromagnet bottom electrode that has a pinned magnetization. You have a ferromagnetic top electrode, the free layer, and the free layer's orientation can cant as it feels the stray fields from the bits that it's flying over. A higher resistance state for bits with magnetization going into the board, lower resistance state for bits with magnetization coming out of the slide. So this is how the data is read back using a magnetic tunnel junction in the head of the hard drive. The other application, certainly not as prevalent as the hard disk drive, but this here is magnetic random access memory, and specifically toggle Imram. And here in this memory, the magnetic tunnel junction, it stores 1 bit of data, 0 and 1, depending on the relative orientation of the free layer to the reference layer. The magnetic tunnel junction is located at every intersection of the word line and bit line in this crosspoint architecture. Now, a magnetic field, a local magnetic field, is generated by passing a current through the word lines and bit lines, and this local magnetic field is what is used to write the magnetization of the free layer. So this technology uses aluminum oxide tunnel barriers. And so now I will introduce spin transfer torque Imram. So as I described in toggle, it uses a magnetic field generated by current passing through the word lines and bit lines, and that's how you write the free layer magnetization of the magnetic tunnel junction. So this type of writing scheme does not scale well to small dimensions. Whereas for spin transfer torque Imram, it uses the current generated from a transistor to write the magnetization of the free layer here in the magnetic tunnel junction. And this type of writing scheme, it does scale well to small dimensions. And that's easy to see here on the far right side. In this top-down SEM image on the far right, I'm showing 16 perpendicular magnetic tunnel junction bits. Each one of them is about 60 nanometers in diameter. And 16 of these bits occupy the same area as just one toggle Imram bit. So it's easy to see here that it's with spin transfer torque Imram that we will achieve a higher density magnetic-based memory. And indeed, there are already Imram products available now. This is embedded Imram product. And the current application is that they are replacing embedded flash. And they can do that because embedded Imram scales better to the 22 nanometer semiconductor technology node and beyond, better than embedded flash does. So we have these Imram makers partnering with these major foundries and manufacturers to make embedded Imram chips. And this has happened in the past 5 years. So let's have a closer look. What is an STT Imram cell? It is made up of the magnetic tunnel junction, one tunnel junction, and one transistor. And the transistor supplies the current needed to switch the free layer magnetization to be parallel or anti-parallel to the reference layer, giving you zeros and ones. And there's no magnetic field required to do this. So it's a magnetic device that does not require a magnetic field. And the writing happens by spin transfer torque. So I'll describe this. Here are your 3 main layers of the magnetic tunnel junction, reference layer, tunnel barrier, and free layer. And then you have the current passing perpendicularly through the layers. Initially, it's not spin polarized, but it becomes spin polarized as it passes through the reference layer. By conservation of angular momentum, the free layer feels a torque acting upon it by the polarized spins coming from the reference layer. And if the incoming current is high enough, then this torque will be large enough to switch the magnetization. So spin transfer torque was discovered by 2 theorists, John Slonczewski and Luc Bourget. And I'm showing here the Landau-Lifshitz-Gilbert-Slonczewski equation describing the precessional motion of this magnetization about the effective applied magnetic field. What I want to point out here is that this green term here, this spin transfer torque term that is going to flip the magnetization, it's directly opposing this red term, the damping torque, that's acting to pull the magnetization back toward the applied field, back to equilibrium. For this reason, we want to engineer the free layer material to have a low damping constant alpha so that we can have the most efficient spin transfer torque to flip the magnetization. So by spin transfer torque, this is how you can operate this magnetic tunnel junction by using a current or applied voltage and without a magnetic field. So here's how this works. This is resistance versus voltage. And we can start here at the high resistance state, for example, a written bit of 1, when the two ferromagnets have their magnetization anti-parallel to each other. And you can read this at low voltage. When you want to flip the free layer to the parallel state, you apply a bias high enough to surpass the critical voltage for flipping till you get to the low resistance state, for example, a written bit of 0. Then when you want to write back to the high resistance state, you apply a bias in the opposite polarity, large enough to flip the magnetization back to the high resistance state. If you take this same tunnel junction and just for demonstration purposes, you want to flip it by magnetic field, then you will get the resistance versus magnetic field curve shown here on the right. Again, these two well-defined parallel and anti-parallel resistance states. And the reversal of the free layer happens by a couple different mechanisms, depending on the size of the bit or the diameter of the bit and the magnetic properties of the free layer. So for very small bits, 25 nanometers and smaller, the free layer reversal happens by coherent rotation. It's as if the free layer, the magnetization of the free layer rotates as a single domain. So this is shown here on the right side. This is a micromagnetic simulation showing these reversal mechanisms. So this is coherent rotation, the red being magnetization pointed up, and then the magnetization rotates as a single domain till it's all pointed down, this blue color. For bit sizes 25 nanometers and above, the switching happens by domain wall nucleation and propagation, and that's also shown here in this micromagnetic simulation here, showing that a domain wall has nucleated in the center and it propagates outward until you get total magnetization down. And you can see that domain wall reversal it takes longer. This y-axis here is time. It takes longer than coherent rotation, and it especially takes longer if you have a free layer material with a low exchange stiffness compared to a free layer material with a higher exchange stiffness A. So for this reason, if we want to have a fast and high density memory, we need to be in the reversal regime where you have small devices that where the free layer flips by coherent rotation. So my role in the Imram research team at Western Digital is to do the sputter deposition and characterization of the Imram stack. And so I want to share with you a couple of tricks that we use day in and day out to make high quality magnetic tunnel junctions. And this trick here is used in manufacturing of the tunnel junctions that are used in read head of hard drives too. So this trick addresses the question, how do you get epitaxial cobalt iron MgO interfaces? I had described to you that this interface is critical for high TMR. How do you get that in a manufacturable process? So this trick here was published in Applied Physics Letters in 2005. And what we do is we start out with a cobalt iron electrode, but we make it amorphous by alloying in boron, 20 to 30% boron. And then we do a sputter deposition of the MgO tunnel barrier onto the amorphous surface of the cobalt iron boron electrode. So fortunately for us, when the MgO, which has a rock salt crystal structure, when it's deposited on an amorphous surface, it takes the desired crystallographic orientation that we want, this 001 orientation. Then we put the cobalt iron boron amorphous electrode on top. After the deposition, we do a post-anneal step. And during the post-anneal, the boron atoms diffuse away, allowing the cobalt and iron atoms to arrange themselves on the crystalline template already established by the MgO tunnel barrier. And this process is called solid phase epitaxy. And this is how you get coherent arrangement of atoms across the interface that gives us high TMR values. The other trick I want to share addresses the question, how do you get cobalt iron with perpendicular magnetization? Because cobalt iron really, really wants to be in plane. It wants in plane magnetization. And indeed, for the tunnel junctions used in reed heads, these tunnel junctions do have in plane magnetization. But for spin transfer torque Imram, we want perpendicular magnetization. And so to get this trick was independently discovered in 2009 by a couple groups and then published shortly afterwards. And the trick is to thin down the cobalt iron boron layers. As you thin down, at this interface of the cobalt iron boron and the MgO, there's a perpendicular magnetic anisotropy generated at this interface from orbital hybridization between the iron and the oxygen atoms. And so this is an interfacial perpendicular magnetic anisotropy. You can see here, as you thin down the cobalt iron boron layer at about 1.5 nanometers, you get this crossover in anisotropy from in plane to perpendicular. Okay. And in fact, conventional STT-MRAM structures now put an MgO cap layer at the top. So you have the cobalt iron boron free layer on top of a MgO barrier with an MgO cap. So then you have interfacial perpendicular magnetic anisotropy generated from both interfaces to further enhance this effect. So let me review these critical performance parameters of the STT-MRAM. So we talked about the writing. This happens by spin transfer torque, and it's characterized by a critical switching current density, JC0. And I want to point out that the switching current density is largely dependent upon the magnetic properties of the free layer material: saturation magnetization, anisotropy field, damping parameter, and free layer thickness. The reading, this is done by the TMR ratio, also very highly materials dependent. This is why we work with the cobalt iron MgO materials system for high TMR. Retention, this is due to the perpendicular magnetic anisotropy energy. So retention is how well can the free layer retain its written state up or down before the magnetization is lost to a thermally activated reversal. So this is characterized by the thermal stability factor delta, and it's usually reported in units of time. How many hours or how many years before you get flipping due to a thermally activated, that's a thermally activated reversal. And endurance, the number of write cycles reached before a specified failure rate. For example, a failure rate of 10 parts per million. So it's basically how many times can you pass a very high current through this very thin MgO tunnel barrier before you get a breakdown of the tunnel barrier causing a short. And that's the expected failure mode in STT Imram. And the different products will require different specifications, different values for these specs. So, and you can tailor the Imram stack for these various applications. So for example, here, the Imram stack that is used for embedded flash replacement, this uses magnetic tunnel junctions that are 40 nanometers in diameter and above. The retention spec is typically 10 years at an elevated operating temperature, write currents above 100 microamps, TMR above 100%, and endurance about 1 million cycles. If you want to tailor the Imram for a standalone application, for example, a DRAM replacement, so this is a high density application requiring magnetic tunnel junction sizes that are 20 nanometers and below, write currents that are very small, less than 20 microamps, TMR values approaching 300%, and endurance 10 to the 12 cycles. And the reason why we would want such a high performance memory is because we are now in an era of big data applications that has massive storage and performance requirements. For example, our devices are becoming more and more connected on the Internet of Things. In big data analytics, this is touching several sectors of our economy, retail, healthcare, and finance. And a popular application here in the Silicon Valley area where I am is self-driving cars on the road. And that requires real-time processing of visual data. So these applications require an effective memory hierarchy that's fast and low power, and it's driving the need to bring this high performance memory closer to the computing unit. So this is motivating our research into new physical mechanisms like spin transfer torque to store information better than the memory options we have available to us now. And this brings me to what are the challenges for making a high density STT Imram. Okay. So I'm talking about Imram cell sizes that are 20 nanometers and below. So these are much smaller bits than what's available now in Imram products. And already when you're making smaller bits, you're losing volume, V here, V for volume. That means you're automatically going to have a lower thermal stability. So which means that you'll lose your data retention. So to compensate for that, we want to increase the perpendicular magnetic anisotropy, but we should do that, but still keep the switching current density low. We need to have low switching current because very high currents will cause breakdown of the MgO tunnel barrier and will have endurance problem. But also, as I described, STT Imram cell is one tunnel junction to one transistor, and very small transistors can only supply very small current, but yet we need enough current to flip the free layer magnetization. So this is a very difficult trade-off for anybody working in Imram, this trade-off between thermal stability for retention and low switching current. Okay. The other challenge is this one here is the fabrication challenge. How do you make these very small Imram bits, 20 nanometers or smaller, and do that at tight pitch or with that's needed for a high density array of bits? And to do that while maintaining tight distributions of these various performance parameters that I described. So for example, when you have very small bits, you can expect wider distributions from these small sizes. And so this wider distributions will lead to read errors. So we want to compensate for that by making the read signal really high, which means TMR needs to be even higher than what we have now in products. So the first experiment I want to describe addresses this challenging trade-off here between thermal stability and low switching current. And because if you're going to increase perpendicular magnetic anisotropy by increasing saturation magnetization and anisotropy field, that's also going to increase your switching current density. So for this reason, keeping the damping parameter low is critical. And so I'll describe our work to engineer the free layer to have low switching current. So the free layer conventionally is about 20 to 24 angstroms thick. It's made up of cobalt iron boron alloy on top of the MgO tunnel barrier with MgO cap at the top. And somewhere inserted in the middle is typically a heavy metal spacer. In this study, it's tungsten. And the purpose of the tungsten is to give the boron atoms a place to go when you're doing this post-anneal step. You want the boron atoms out of the way to allow this solid phase epitaxy of the cobalt iron and the MgO to get high TMR. The boron atoms want to diffuse to this heavy metal spacer. Otherwise, having this heavy metal here is going to degrade your magnetic properties of your cobalt iron boron. It's going to reduce the saturation magnetization and increase the damping parameter. So we want to minimize how much tungsten is needed there. So our strategy for doing this is just to altogether reduce the thickness of the free layer. And we were able to reduce it substantially down to 12 angstroms here, and so that the tungsten layer is very, very thin. And we found that the magnetic properties improved even further if we take this single tungsten spacer, keep the same thickness, but then split it into two thinner layers. So still, this is, for example, a 12 angstrom free layer. And here in this cross section, I'm showing a 13 angstrom free layer with the MgO barrier at the bottom and the MgO cap at the top. So we proceeded to use this type of free layer design here with these two tungsten spacers. And we made a free layer thickness ladder. So the thickest free layer in our study was 17 angstroms, and then we thinned down to 13 angstroms and then 12 angstroms. By thinning down the free layer, we reduced how much tungsten was necessary to keep perpendicular anisotropy of the free layer. By taking out a lot of tungsten, we increased substantially the saturation magnetization. The damping parameter was already low to begin with. By taking out this heavy metal, we reduced it even further. And the exchange constant A increase so that it approaches values we know for bulk iron. So this is to show that these very thin free layers here have very good magnetic properties. So we proceeded to make bottom pinned STT Imram devices with this free layer thickness ladder here. And the diameter of these devices using optical lithography is in the range of 55 to 130 nanometers, and the TMR values approach 125%. And the coercive field for switching the free layer, switching the MRAM bits reached 2.6 kiloorsteds for the smallest devices. Okay. So what we wanted to know from the study is this trade-off between the thermal stability factor and the switching current density. So here, the thermal stability factor delta, we found this from field switching probability measurements, and we fit the results to a domain wall reversal model, because with this size of devices, we know that we're in the domain wall reversal regime. And this analysis gives us domain wall width, domain wall energy density, and the thermal stability factor, which is found by taking the domain wall energy density multiplying by diameter and film thickness over KBT. And what we find is that it's these thinner free layers with the better magnetic properties. They have domain wall energy density that's a lot higher, and this brings us a high thermal stability factor, even though the layers are very thin. The critical switching current density JC0, this was found by fitting pulse width dependence of the critical voltage using the thermal activation model for spin transfer torque switching. And what we found is that these thinner free layers, they have 30% reduction in the critical switching current density compared to the thickest free layer of our study, this 17 angstrom free layer. So then if we look at spin transfer torque efficiency, this is a common figure of merit in Imram. It's defined as the thermal stability factor delta over the critical current. We find that it's the thinner free layers that have the highest efficiency because they're showing the lower switching current density, yet maintaining high thermal stability. The other experiment I want to describe addresses this nanofabrication challenge. How to etch Imram bits at tight pitch. And at Western Digital Research, we had the goal of making a 50 nanometer full pitch array of Imram bits, showing that the bits are physically separated and doing an electrical test to see the free layer switching. And by 50 nanometer full pitch, this means the distance between the center of one Imram bit to the center of the neighboring bit. Okay. So looking at the Imram studies and literature, there's a lot of great reports of very good performance of Imram bits that are very small. For example, from the IBM Samsung team, this is an 11 nanometer bit. Here's a couple of examples of 20 nanometer diameter bits of good performance, but these are isolated bits, meaning that you have your Imram pillar here, but there's no neighbors close by. There are very, very few reports of studies reporting of arrays of Imram bits at tight pitch. And the reason is because they're very difficult to fabricate. To make a Imram bit, you need to remove a lot of metal material by milling. And this metal material, when it gets removed, it gets redeposited on the sidewalls of the pillar and it shorts out the barrier so that you get nothing but shorted bits and no electrical data. And that's what happened here for this Samsung demo here. They have the tight pitch array, but with all the sidewall redeposition, there's no electrical data. The best demo that we know to date, and this is already back in 2016, this is a 4 gigabit demo from SK Hynix and Toshiba. It's an array at 90 nanometer full pitch with electrical data. But if we want to be competitive with DRAM, we need to achieve at least a 56 nanometer full pitch. And so this is the experiment that we carried out in our research lab, starting with blanket magnetic tunnel junction film and the hard mask on top, the hard mask for protecting the magnetic tunnel junction during the milling process. And the hard mask was defined by E-beam lithography step. And then these hard mask pillars were made by reactive ion etching. The hard mask is made up of tantalum nitride, diamond-like carbon, and chrome. And then I'm showing here this tilted SEM image of the hard mask pillars. This is a tilted SEM. This lower one is the top-down view. And you can see there's a high aspect ratio of the hard mask with very vertical sidewalls. So this is what's absolutely critical for a good hard mask. So now using this hard mask, we're ready to mill into the Imram stack. And we do this by ion beam milling, first at low angle to etch into the depth of the stack, and then at high angle. And now remember that the wafer is rotating during this process to mill away the redeposited material on the sidewalls to prevent that shunting. And so here's a tilted SEM image of the final tight pitch array after milling. But now we want to do electrical measurement, and we don't have easy access to very expensive CMOS. So we do the best we can in our research lab. And we came up with a bottom point contact vehicle so that we could electrically measure these bits. And so I'll describe the bottom point contact. You start out by using E-beam lithography to define the metal pillars here, and a second E-beam lithography step to make the contact arms that go out to the contact pads. And then we do silicon oxide dielectric refill and a chemical mechanical polishing to make sure this surface here is very, very smooth for the Imram stack deposition with the hard mask on top. And then we make the Imram pillar array using the process I described previously. We do a spin on glass for planarization, and then a common top electrode over the array, so that at cross section, this is what we expect here, but I can show you in our real images what we ended up with. Let me get this banner to disappear. Okay. On the left, I'm showing the SEM images of the bottom point contacts. This is 4 pillars, and then with the arms going out to the contact pads. And then on top of these 4 contacts, here is the Imram array put on top, and we take a diagonal slice here to get these cross-section TEM images I'm showing. At the top is a 52 nanometer full pitch array, and the lower one is a 50 nanometer full pitch array. And with these images, you can see very good alignment of these multiple E-beam lithography steps to get the contact pillars and the arms and the bits all lined up. We confirm physical separation of the bits. We see that we have removed the redeposition of the sidewalls because we can perform the electrical test and confirm good magnetics by seeing a TMR value of 100%. Okay. So this brings me to the conclusions of my talk. What I wanted to show you with this lecture is that we are all using magnetic tunnel junctions pretty much on a daily basis to store our data. And this is a result of major discoveries and breakthroughs at the basic research level over decades. For example, the demonstration of spin polarized tunneling for the first time, and then 20 years later, TMR at room temperature, and then even very high TMR with MGO tunnel barriers. We continue to make advancements, such as the discovery of spin transfer torque that allows us to switch magnetization without needing a magnetic field. And this has given rise to emerging non-volatile memory technology, which is spin transfer torque Imram, and there are products of this available now. So to push this technology even further to a high density SCT Imram, we need further innovation in materials and fabrication and memory architecture to push the cell sizes to 20 nanometers and below with very good performance. So I just want to thank the IEEE Magnetic Society for giving me the opportunity to talk about our research at Western Digital. And I want to thank these folks here that have inspired me to put this lecture together. And thank you very much for your attention. I'm happy to take your questions.
Now the session is open for question.
Thank you, Tiffany, for the very interesting talk. I particularly like the way you narrated from the history and developed all the way to the latest achievements. So it helped me to understand some of the gaps in my understanding of history.
Great.
So I'm particularly interested about slide 11, where you showed someone demonstrated 27% TMR. May I know who is it?
All right.
Slide 11. Yes.
You looked very closely at the plot, it seems.
Yes, yes.
Oh, 27%. The reference here says a CNRS group.
Okay.
But the specific details of that study, I'm sorry, I don't know. But it looks like it's this very initial MGO tunnel barrier work.
No one talks about that one. Okay, then my second question is about the slide 23.
Yes,
So these simulations were done in cobalt and boron with the PMA.
that's right.
Okay, thank you. That's all from my side. There are some
Yeah.
more questions.
Yep, specifically the reversal processes for perpendicular cobalt iron boron. Yep. Spin
Okay.
transfer torque.
Okay.
Hi, Tiffany. I also have one question.
Okay, continue on.
Yeah,
Hi.
it was regarding the redeposition of the agents. I mean, like after we do the iron milling, like there will be redeposition that leads to shortening of the MTZ.
Yeah.
So in this case, like you use 3-layer hard mask in order to actually avoid that issue. But my point is, because I am also facing this current issue, I mean, to getting shorting of the layer. So how can we remove this 3-layer mask, I mean, without any leaving any impurities on the sample itself?
Yeah. So a lot of this hard mask does get consumed by this process because you're milling a lot deep into the stack. And so this is the reason why we have the tantalum nitride layer here as this layer just above the Imram stack. Tantalum nitride is going to be conducting electrode for us, and this is where we're going to make contact from the top. So that's why we end with this layer. So pretty much the chrome and carbon layers are gone, and a lot of this tantalum nitride is consumed. There's some left, and this forms the basis of our top contact.
So following this question, like why can't we directly take a very thick layer of tantalum nitride itself?
Its resistance to this milling process is not strong enough. So the purpose of using this diamond-like carbon is a material that's more resistant to the milling. It'll last longer, allowing you to mill deeper.
Okay.
Yeah.
Thanks.
Hi, Tiffany. Abhijit here.
Hi.
Can you hear me? Hi.
Yes.
I have a question on the STT Imram part. Usually, what we see is that the damping parameter in general it goes up when the ferromantic layer thickness goes down. So what I see in this case is very interesting. So what can you tell us a bit more about the possible physical origin of why? By the way, is it intrinsic damping or the total damping that you are showing here, or that doesn't matter?
This is a film level damping that we get from a FMR study of a blanket film sample.
Total damping, right?
Yes. So the damping measurement gives us this damping parameter, the effective anisotropy, and also an inhomogeneous broadening.
Yes, this I understand. So can you tell us a bit more about why the damping is improving? I mean, the physical origin.
Yeah, I'm definitely aware of the studies that do show that as you get to very thin layers, the damping parameter actually goes up. And so this was something we were looking out for in our study, and we are fortunate to see that here, even we're very thin and the damping value is still low. However, if you do go lower than this, you start to see it go up. Here, what we're finding is that we're starting already very low. We have this effort to have very good magnetic properties. You see that the MS is very high. We're taking out this heavy metal. This is what's driving the damping parameter lower than already what's low. But I do know that if we do try to push and go smaller than this, then we start getting a increase of inhomogeneous broadening, increase of damping parameter.
Yeah, definitely. This is just 1 nanometer almost.
Yes.
The other question I have is, so the boron diffusion is already known to the community. Was it deliberately? I mean, the choice of cobalt iron boron, was it deliberate to leave out the boron and make it better crystalline structure of COFe? If not, then why not to directly use cobalt iron and not cobalt iron boron?
Okay. The boron is necessary to do this trick of a solid phase epitaxy using a sputtering process, a manufacturable process. So
Yeah.
this is why we deal with the boron. Now, your question of what happens if you leave the boron out.
No, the question is why
mhm.
why don't you directly use cobalt iron instead of
Okay.
cobalt iron boron? Is it that by using cobalt iron boron, and when you leave out boron by annealing, you achieve better epitaxy?
So the layer that's closest to the MgO layer, the cobalt iron boron layer that's closest to the MgO layer, you need it to have this boron to achieve this solid phase epitaxy. Okay. That if you actually look at this paper here, this is my paper, Journal of Applied Physics. I go into detail, and I actually do use layers of cobalt iron that don't have boron. But again, right at the interface, it's the free layer starts out with a cobalt iron boron layer because you need to have this solid phase epitaxy to happen. But then the upper layers away from the barrier, it has just cobalt iron, no boron. This is actually how you achieve very high MS values that I'm showing here, because there are some parts of it that intentionally don't have boron in it. Yeah.
Right. Yeah.
Yeah.
Thank you very much for the answers and yeah, for the presentation as well. Thanks.
Thank you. Thanks for your interest.
I have a very generic question. So recently we see that Apple and other companies using SSD in place of HDD. So how long will using SSD in place of magnetic drives? I mean, when the magnetic drives will come again and replace SSD?
Oh, so they're both going to coexist, which is excellent for Western Digital, right? So hard drives are going to be around for a very, very long time because they have the lowest cost per gigabit of storage. And this is why the 90% of data in data centers is stored on hard drives. Hard drive is the king of the data center. So now, but SSDs will be around as well because they have faster performance, but the cost is significantly higher than the HDD. So there's a place for them in the data center or in your devices for both of them. When you're ready, when you need the fast access, faster speed and performance, this is where you use your SSD. Then when you're ready for mass data storage, this is where you have your HDDs.
Thank you.
Yeah.
And I think there is no other question. Thanks a lot for the talk, and let's thank the speaker.
Thanks so much for your interest.
Thank you, Tiffany. Thank you for joining again.
With this, this first session is closed, and after break, we shall start the session again.
Great.
Ramu, you can end this.
Yeah, so we will meet at 10:45. Yeah, we'll be back. So I will close the session.